Oh, okay. Let's start.
Okay. I'm going to share my screen. So my name is Boaz Raz, and my project was an object recognition acceleration using 8-bit quantization with the Google Edge TPU using drones. So again, just to mention it again, the problem was since drones are being used more and more in surveillance, rescuing, mapping, and military, the need for autonomous drones and using their camera for object detection is increasing nowadays. And since big LiDAR and radar are heavy and expensive, my project or my idea was to find a better way and a lightweight solution for this. So my approach was using the Google Edge TPU. So it's a small board that takes, as you can see, 0.5 watt for its computation. And it looks something like this. So most of my presentation is a demo. So hopefully I can load it. So you can see it's a very tiny board, just to show the whole thing. So I connect the whole thing for the TPU to a screen, a separate screen, and it loads it just like a lightweight Linux. And it has just this simple UI and a terminal. So at first I want to establish kind of a baseline to see how the detection works. So I connected to a camera straight to it and loaded some the MobileNet SSD with the Coco labels. So it has, I think, 88 or 89 objects just to get this thing going. So there was I had a lot of challenges within this project. And you saw the first one was very busy image. So once you can play with the threshold, the default was 0.1. So once you go to, obviously, if you go up, it clears the detection. So some challenges I had was like the first few weeks is just to get familiar with the TPU, install the operating system, play with it, do some testing. That was like the first 2 weeks. Here I'm just like kind of SSHing to the device. I'll show you here in a second. And the camera was just to establish some sort of a baseline to see how the TPU works before continuing on with the drone. So the first few weeks were setting up the environment, doing some baseline like you saw with the camera. Once I felt comfortable that the rest can be done, I kept on working on a challenge to the drone. So here I'm just using the example MobileNet SSD. And the reason I use that, and you can see by default, that's what I used earlier. I used the external camera, but you can see here I'm using the UDP, and that's gonna be for the drone. Another challenge was sending the UDP signal to the TPU. For some reason was very slow. So you see the comment that code, I'm gonna uncomment it later, was to shrink the frames trying to overcome some video delays. And here is the basic object that come with with the MobileNet 89. Another challenge was in my previous project or different project, I used like different Python packages to stream and control the drone. For some reason, I couldn't find why. It didn't work with the TPU. So unfortunately, I had to come up with this solution that you see now to get us the video streaming from the drone. So that was another challenge I had to deal with at the beginning. And then like some buffer issues because of the data that was sent to the TPU. And that was just to get to this part. So a lot of work before I actually could deal with the drone. So once you start a drone, you have to connect to the drone internet. So it takes a second. So here you can see that I am connected to it now. So when it is connected, you have to connect to the drone itself. That's based on the it's a Telos, so you have to like establish the UDP connection. It has 2 ports that is connecting, and you stream it. So once it's streamed, then you run the script that you saw earlier. I ran the script that you see earlier. And this is how it looks from the drone. So it's actually sending the signal to the Google Edge TPU, run the object detection in real time. And you can see again, the image is very busy. It's a little big, it's bigger. It's before I shrink that. But overall, I was very surprised and happy beside the delay from the, can you see my screen okay?
Yeah.
Okay. I was very happy with the speed of the result compared to my previous project when I ran it on like, 1080 GPU and an i7. So I was very surprised that this such tiny device I was able to get this result. So, and what I did here instead of, just a moment. Instead of controlling it via the command line, which I could, but it was a bit harder, I just connected to the app just for the proof of concept. So you can see I can fly it, send the signal to the TPU, run it on the 8-bit quantization model, and stream it to the screen. So there's a lot of going on from this, just from this little device. Another problem I had, and the reason I used different models, I was trying to convert the YOLO V3 model I had to use it for the TPU. It took me a long time to do that. And unfortunately, that didn't work. I mean, the conversion worked, but when I tried to load the model to my script, something didn't work. I couldn't figure out, but I spent so much time on it that I decided to use like a different model. Again, just to do the proof of concept. And here I think I increased if I'm not mistaken, the threshold. So here is where I uncomment that, and just to show, I mean, this is frames are smaller. It's a bit faster, not much. But again, it was just to try some other things. Let's see here. So I had to compromise a lot within this project, you know, using different packages that I used before, control it differently that I used to. Make sure. Let me see. So here you can see once I, it's just doing a different object, but let me see. I was trying to load some other models here, just a moment. Oh, so here, my point to show is like, so the model I ran was especially for the TPU, but if you run it not for the TPU, it's a lot slower. So if you run it on the CPU, there is much larger delay. So you can right away see the benefit of quantizing the data with the same device versus not. So here is some models that I play with. So the next one, I just did like some face detection, quantization. Again, you can see there's like the one for the TPU and the one, just the one for the CPU. So a lot of work around. So now it's just facing, doing that, the face detection. And yeah. I mean, so all in all, I was happy since it was just, like I said, proof of concept to see how I can move from a big device that runs the object detection on a live stream to a small factor and do almost the same thing. For me, it was kind of surprised. Unfortunately, you know, dealing with new technology, there are a lot of workaround you have to do since not all packages are compiled for that. So it was always like, I felt that like I got closer and then I had to kind of go around to try different things to get to what you guys saw. So.
Yeah, yes, I believe this is a very interesting project. Yeah. Any question to him?
Thank you.
Yeah, I had one. I was curious how much the TPU cost, or is it like on loan as like a student project or something?
I think I can send you a link. I think it was like 160, something like that. But what I was trying to do, and I ordered it, but I didn't get it. They have also a USB TPU, and I didn't get it because they were out of stock. I just got an email that they're going to ship it in 2 weeks. It's too late for the class, but I'm curious to see if I will have that UDP delay on the USB, since the USB I'm going to connect to my laptop and run the same script still on the TPU, but the rest of the processing, like the open. So the screen you saw was the OpenCV. So the OpenCV maybe needed like a better graphic card just to show it. I'm curious about it. I can update you, but that was my my one thing I was curious about. I thought maybe it was like the delay was caused by a network, but the network device on the TPU. I wasn't sure. I tried to do a different network device, meaning a different Wi-Fi device. I couldn't get it to work. but yeah, I was thinking 160, something like that, 169. But it's I was surprised how powerful it is, and yeah.
Yeah, very cool.
Yeah.
Next group, please.
I think Ryan, I can go.
Yeah, I'm ready.
Yep, I'll share my screen.
Okay.
All right, hopefully you guys can see my screen now.
I can.
Okay, take it away, Ryan.
Yeah. Good afternoon, everyone. So welcome to our final project. So today we would be talking about Shift CNN, its implementation and evaluation. So this has been inspired by a paper titled Shift CNN: Generalized Low Precision Architecture for Inference of Convolutional Neural Networks by Dennis A. Gudowski and Luca Rigazio. So yeah, so let us begin. We would be talking about the following things today. We would start by describing the problem. We would be talking about why it is relevant, and we would move on to how we solve it. So one of the key concepts involved in the solution is called quantization. We would be talking about a toy example, which is a very minute proof of concept kind of example that we are implementing using VHDL. Then we would be talking about basically the implementation part of it, divided into a few steps. The first step is how we get to a pre-computed tensor from the Shift ALU, and how we store that. Then we move on to explaining the adders, the array of adders, and the control logic that basically controls the flow of data in between those adders. Then we would be moving on to talking about the implementation results, basically from the various test benches that we have built. We would finally be talking about the problems that we ran into, the limitations and the challenges that we faced on the way. And finally, we would be talking about the schedule, which is basically like what we planned to do initially and how much of it we have achieved. Can I have the next slide? Yeah. Okay, so this is the problem. First of all, let's talk about what the problem is. So as you can see in the diagram given on the bottom right, so this is basically a convolutional neural network developed by Google. All those blue colored boxes basically indicate the convolution components of this neural network. One of the key one of the key elements of this convolutional element is basically the MAC operation, or the multiply accumulate operation. So what we are trying to do here is we are trying to come up with a cheaper and a more efficient way to do the MAC operation, as in to achieve the result of the MAC operation without actually doing it, so that we can basically accelerate this hardware and make the whole process much faster and much more efficient. Yeah. So why is this problem important, or how does this make it relevant? So first of all, this is it's really an up and coming field, because a lot of research has been undertaken in this area in the recent past. And it's essentially towards the implementation for embedded systems and data center deployments. One key advantage of this technology is the fact that you don't really have to retrain a model after when you want to shift to this technology. You can just use a pre-trained model, and using the proposed quantization algorithm, you can just shift it to this architecture. And there's just a 1% drop in accuracy, which is very impressive, given the fact that it makes it almost 2 times more efficient in terms of speed. And architecture is also more suitable to be extended to privacy sensitive applications. So we can basically replace the expensive leveled fast homomorphic encryption and with cheap LTFHE shifts that make use of encryption techniques like homomorphism. Yeah. Next slide, please. Okay, so now let us talk about the solution or how we approach this problem. So the most important concept associated is called quantization. Now, quantization basically means that we have to pre-compute certain values if we want to replace a multiply accumulate operation with additions and shift operations. So there are certain things that we have to pre-compute, and we have to store these pre-computed values so that we can do that. So when I say quantization, what I mean is that it's basically we are reducing the inputs that we have to powers of two representation. So for example, if I have an input which is 10, I would be storing 10 I would be storing sequentially the following numbers: 10 minus 10, then 5 minus 5, then 2.5 minus 2.5, and so on till basically 2 raised to b minus 1 terms. So just to give you an idea about what those variables mean, b is basically the bit width of the codebook index. M is the number of possible codebook index combinations. So as I said, like 10 minus 10, 5 minus 5, and so on till 15 elements are there. N is the level of quantization. So basically, if I have to express an input in terms of in its quantized form, then I would be using like two terms from the pre-computed list of things. So basically, if you increase quantization, you are getting closer and closer to your accuracy because your operations are becoming more and more accurate. But at the same time, there's a increased memory overhead. You have to store more pre-computed terms. So yeah, so that's basically where there is a memory versus efficiency kind of trade-off. N into B is basically just the multiplication of the levels of quantization and the bit width. And P is basically the number of possible product terms that can be pre-computed. So yeah, that can be given by the formula M plus 2 into N minus 1, which is 17 in this case, including 0 and identity. So this is our toy example. This is what we have been trying to implement, and we successfully implemented in this project. So I'll just briefly tell you what is going on here. On the left side, you can see those three columns, which are basically the channels. There are three input channels. So with a width and breadth of 2. So that is 2 into 2 input channels. Then we have two sets of filters. So one is basically 0, minus 1, and 0.234375. And the second one is the one you can see towards the right. So what is going on here is you're basically multiplying 1 into 0 plus 5 into minus 1 plus minus 3 into 0.234375. And you're getting your first output term, which is minus 5.703125. And similarly, you're doing the same with the second filter, and you're getting the second output term, that term. So that is what is going on, and we are doing it for every single one of the elements. And so now you have an idea of what the array of adders has to do. You also have an idea of what are the terms you have to pre-compute. I'll give you just a very simple example of how we do the pre-computation. So if you think about the 0.234375, now to pre-compute that, what I would be doing is I would be saying that let me first store. So basically, the multiplication I have to do here is 1 into 0.234375. So I have pre-computed 1 divided by 4, which is basically my fourth term. So it is basically 0.25. So I would be taking that term. Then also I also have a 1 by 64 term. So that is going to be that is going to be my 12th pre-computed value. So that is something like minus 0.001 0.01625. So I'm going to be adding 0.25 and minus 0.01625 to be getting 0.234375. So that is how that works. Yeah, okay. So you have a basic idea of what we're trying to implement now. Now let's move on. Okay, so this is basically the architecture of the things that we're trying to implement. We start with an input tensor, which basically has like 3 dimensions. One is the channel, which is 3 in our case. Then there is a height and width, which is 2 and 2 in our case. Then we basically pass this input channel as input to the shift arithmetic unit, which is basically performing a series of shift operations and sign flips. So if the first element that comes in is 10, as I mentioned earlier, the first operation would basically do like a sign flip. So minus 10 would be stored. Then there would be a shift operation, which would basically get you a 5, and then again a sign flip, and so on, right? So that is what is going on with the shift arithmetic unit. Once we have got those values, we are storing those pre-computed tensors for further use. We are going to be using those pre-computed tensors in our array of adders to be getting to those results that you can now imagine using the toy example. Bias is basically just the term that you like. It's like um, there are a series of multiplications that we are performing, but at the end of it, you also want to add a linear term to it. So that is why we have a bias term that we're adding to it. Yeah, and finally, what we really want to achieve is to get that output tensor, which was basically, in our case, it was a 2x2 matrix. There were like two 2x2 matrices. Yeah. So this is basically a test bench that demonstrates that we have been right so far, and we got the results that we expected from the shift ALU. So if you can see, the 3 input terms here is -4, -4, -4. And then we have we are trying to multiply that with 2 minus, not multiply, we are trying to basically generate a pre-computed value with weights 2, -2, and 3. So those are basically the indices of the pre-computed tensor that we have. So basically, when you're seeing 2, what I expect is that the result has to be -2, because you're saying that it's basically like 2 shift operations is what is happening. So it's like the first value will be -4, the second value would be 4, the third value would be -2, and which is what we are getting in the output. Again, if you're doing if your input is -4 and your weight is -2, then in that case your output is 2, which is basically like you just do a sign flip and you get 2. Then again, if your input is -4 and your weight is 3, then you get a -1. So I guess you have an idea of what is going on here. Yeah, take it away, Anthony.
Okay, all right. So I'll be finishing off the rest of our presentation. So what Ryan mostly covered everything that we were able to make before our midterm presentation, and the rest of this covers everything that we've completed between then and now. So after we've pre-computed the pre-computed tensors and stored them in an array of shift registers for storage, the next thing we're going to go to is our array of adders. So we see the inputs are the weight tensor, which are those quantized weights that we discussed earlier, the biases, and the output is the output tensors. So this is kind of a zoom in level on the array of adders. So the inputs are the pre-computed tensors for the separate input channels. So in our case, we have 3 input channels. So we have 3 pre-computed tensors going into an array of 3 multiplexers. And then we use the weight tensor as the selector for these multiplexers to select the correct value from the pre-computed tensor. We sum them up with an array of adders along with the value that's in the output tensor output register already. And that's how we get our final value along with the bias. So to do that, we have to implement some control logic. So if we take a look at algorithm 2 here, this describes the control logic that we had to implement. So on line 1, we're looping through every input value. We're reading the 3 channels for that input value and computing the 3 pre-computed tensors and storing them in our array of shift registers. And then on line 4, we're going to loop through the output channels. So in our case, we have 2 output channels because we have 2 filters. You would write the bias to the output tensor. And then for each level of quantization, in our case, we have 2, we're going to loop through the values of the filter, select the correct value from the pre-computed tensors using the weight, and then add them up with the array of adders. So we did this all with a modular design, so we could break up the different components between Ryan and myself, and then we put them all together into a top-level entity that we called ShiftCNN entity. So what you see on the screen here is the behavioral definition of our ShiftCNN entity. You can see the various components that we ended up implementing to make this circuit. So the first thing you'll see here are 3 ALUs, shift ALUs. So those take our inputs and then output the pre-computed tensors. Those outputs are stored into an array of shift register so that they can be used by the rest of the circuit over multiple clock cycles. And then the output of that array of shift register and the input value itself padded with some zeros since we have a 4-bit input, but the multiplexer operates on 8-bit values. Those all serve as the inputs to our array of multiplexers, which finally feeds our array of adders, which is operated by a couple of clock signals and outputs our output result. So here's the grand reveal. This is our final validation test bench of our ShiftCNN circuit. So in the bottom here, you'll see the toy example output that we set out to verify with our circuit. And then on the bottom right, you'll see the order that those values are output based on the algorithm that we just covered. So you'll see output channel 1, value 1's output first, then output channel 2, value 1's output, and then back to output channel 1, back to output channel 2, and so on and so forth. So if you look at the test bench here, you see our simulated ShiftCNN entity. It has 3 input values, which are the channel values from our input tensor. It takes the weight values, which are the quantized weights, and there's a set for each quantization level. And this whole circuit is controlled by a couple of clocks. So we have a reset clock. So on the rising edge of the reset clock, we'll change our output register value to 0. And then the clock, the clock on the rising edge, this is when the output of the array of adders is stored in the output register. And then clock 2 is just used to control our array of shift registers so that the values are ready in time for the rest of the circuit. So for an example here, you'll see our first set of input values here. And then we'll do output channel 1, which is this group of weights here, and then output channel 2, which is this group of weights here. So for output channel 1, for the first quantization level, you'd have 3 weights. So in this case, they were 0, -1, and 3, which again, those are indices, not like multiplication values like Ryan discussed. So when the clock rises, we select those values, add them up with an array of adders, and then store them in our output register. So you see -5.75. And then again, you do the same thing for the second set of quantization weights. In this case, the results were shifted so much that the output was 0, so there was no change. But if we look at the second output channel, we'll see after the first level of quantization, the output value was 3.875. And then after the second output, or after the second level of quantization, we actually add a small term to actually, which changes our output to 3.6875. So that kind of demonstrates how increased levels of quantization give you more fidelity and more accuracy back to your original value had it been a multiplication operation and not shift operations. So we can see here that our values match our expected output. So we have -5.75 here, 3.6875 here for channel 2, and then back to channel 1 we have negative 6.5, and then back to channel 2, 5.125, and so on. So this is kind of our proof that our circuit does what we set out to do. So for our implementation results, we ended up making at least 29 VHDL source files and test benches as we designed and iterated and completed our implementation. Both Ryan and I were new to VHDL at the start of this class, and I think relatively new to digital logic design overall. So not all of these source files are used in our final top level entity. However, a good portion are. A lot of them are components of components that led into that ShiftCN entity. Others are just iterations that we had to make based on design flaws. Like for example, I think I made the array of shift registers the wrong size at least once, maybe twice. So we would have to make a new set of source files to change those. If you're interested in seeing all of our code in detail, our GitHub is public. You can visit that at this link here. And we had quite a few lessons learned, I think, working as a partnership. I think in addition to us both getting the basics of VHDL down and learning some of the more advanced features, for example, like using array types that would allow us to scale our toy example up to a larger example, which we used in some entities, but not all entities, but we were at least exposed to some of those more complex VHDL features. But actually working as a partnership, we learned some other lessons, in particular with the design. At the start of the project, we weren't too careful about making sure that the output of my module that fed the input of Ryan's module were actually the same types and discussed ahead of time. So as we went through the project, we got better at working those things out so that we could connect our components together in the top level entity and get it all to work. So for some limitations, we did set out to try to synthesize our circuit, because in the paper, the authors computed the number of lookup tables and flip-flops and compared their implementation versus a multiplication implementation. And we were hopeful that we could try to synthesize our circuit as well and get those numbers and extrapolate our results compared to theirs. But we simply just ran out of time to finish that. We did click and run the button, and this is the warning or the error that we got when we were trying to do that. It says we need to check whether we've instantiated and connected all of our top level ports. I think if we go back to the original tutorial that was provided us at the start of the course and went through that a little more closely and looked up this error, that probably would point us in the right direction to getting this synthesized. And finally, this was our schedule. So Ryan, what we saw last time is Ryan had the shift ALU in the test bench, and I had done the array of shift registers in the test bench. And then since the midterm update, I implemented the array of multiplexers in the test bench. And then Ryan and I both worked on the array of adders and its test bench. And then I finally did the control logic, the clocks, and the test bench to show our top level circuit worked. Again, we tried to synthesize it. We didn't get too far on that. And then we also ran out of time to try to do some of the accuracy analysis using a GPU. But these are the references that we referred to during this project. And pending any questions, that's all we got.
I believe this is a very good example for two students project. So each one has their own work, and of course their components can be connected. I believe the result shown by Anthony is very good. Eventually he's summarized the whole design and use all the components to demonstrate a toy benchmark. I believe this is very good. So any question for them? For the synthesis, I'm afraid that you need to connect your computer or Vivado to a specific FPGA so that they can use the specific library, physical library of that particular FPGA to do the synthesis. Otherwise, that is impossible for you to do that. And I believe you did a very good job on the logic part. Maybe in future we will try the synthesis.
Okay, yeah, thank you very much.
Okay, next group, please.
I think Trey and I can go.
Okay.
All right. All right, can you guys see my screen?
Yes.
Trey, can you hear me?
Yep.
All right, so this is our project for the convolutional filter accelerator, which basically is just a proof of concept for an MCU on a system on a chip doing convolution versus a hardware accelerator on an FPGA in the same system on a chip, and just kind of comparing them. And so I'm Austin Parks.
I'm Trey Peterson. And we'll first go through the hardware acceleration. So just the overview of what all happened is before we had the convoluter finish, and after that kind of midterm part, we had to implement the stream controller. Just a quick overview of the convoluter is what does the dot product in a cascaded adder, and the stream controller is interfacing with a DMA. And DMA, which is the directed memory access, has to basically, it can interface with the memory on the processing subsystem to pull image data from that all the way over to the hardware without having the CPU to do stuff and basically bog down the CPU in memory transfers. And another thing is the DMA could do like really quick stream speeds and high throughput. Before we wanted to do BRAM as like kind of like a medium to kind of pick stuff out. Quickly learned that constraints in the hardware of that project, it can quickly make you realize you can't use BRAM because you only have 2 data read ports, and that can really slow down your picker, I guess. So to pick your subset. And also, so basically the stream controller is an Axie4 stream, and that interfaces the DMA to our convoluter. So next. Overview of the convoluter, it's a cascaded filter. Reason why we use this, like we said, as opposed to the adder tree, is that this is more efficient to the Xilinx hardware, because this is what they call hard IP, which is a multiplier and adder. And if you could think of it as these things are literally connected vertically. So if we just connect them together vertically, you can eliminate, basically you can eliminate your, I can't think of the word right now, but basically you can increase the clock speed all the way up without worrying about having any adders in the CLB slices. So if you have adders and CLB slices, you'll bog down the system, as opposed to having a hard IP where you can crank up the clock speed a lot more. So that's just for like a future, say, design thing. Anyways, so it does a dot product. You add them together because that's how the dot product works. Next. And that was the test bench. Oh, I had another image. Oh, okay. Anyways, so remember that test bench we had? We had another test bench also, but it wasn't really going to show you much. So that was the convoluter test bench. There was another test bench I had that basically for the Axie stream, and it was failing. And the issue we had for the Axie stream is that, well, it turns out that Xilinx, the stream verification, this is what they call it, is that it basically sends in like test signals. So if we can explain Axie stream, it's like, hey, we're going to send data from the processing subsystem to you. And, we're going to send like 128 bits, which is what we wanted. The issue we had was that when we implemented the convoluter and the block diagram, so go to the next slide, just to kind of see it. So that when the block convoluter was in the block diagram, it turns out that when you create the IP for the DSP48 slice, it just fails in simulation. And that was like a weird thing that like it just kept on failing. And then I was like, all right, screw it. We're just going to implement this in the hardware and see if we can generate a bit stream. It generates a bit stream and it works. And I'm like, all right, I can't trust test benches, at least to some extent, because when I dug down into it with the test bench scope, turns out the convolutioner, the DSP48 slice was just not working, and maybe just how the IP was generated in the block diagram, because there's different generation ways, global, and then there's like the individual output. So I don't know, that was just very painful 2 weeks. So this is the overall block diagram though. We had to collaborate on how we got the data in, and especially like how big our data size was, because we wanted to get in just a whole subset. If we think of a convolution being a 3x3 with a filter, which is 3x3 also, the filter is actually just going to be pre-generated on the FPGA. It was going to be too much effort to really pack it in with it, because it was just too much. We would have to have another stream interface altogether. It was going to be way too wild. So we just had the filter on the FPGA. We had the stream coming in into the DMA. The DMA sends it over to our ComCont in, which you can see as the very left on the big circle. And you can see it kind of splits off into two separate blocks. Now, the top one is axis delay, which is basically, it tells the stream, hey, you're going to have to wait 13 cycles. And this is going to be how long it takes to do a whole dot product in that wrapper below it. And basically that convoluter is going to do its thing. And then the delay is going to wait. And then once it's done, it all comes together and it sends out that result and the convolutioner out. And basically it sends a 32-bit value out. So reason why we say why we're doing a 32-bit value. So if you wanted to do like a Gaussian blur or something like that, you would have to divide by 9 or something like that. So if you do like a 3x3 with all 1 values as the filter, you're going to get like a very large pixel value. But at the end, you're going to divide it by a scalar value of 9. So just output a 32-bit value and have the Python code just divide it. So that way you don't have to use a divider. Anyways, go ahead. So the hardware worked with the implementation without the test bench working. So it was very crazy. But we did have to collaborate a lot with how we packed the bit values, how the DMA worked. Austin helped out a lot with like explaining axis stream, interface data, because I was kind of slowing down a lot. I was like, I need help. And so we had to really put our heads together for him setting up the processing side of how does he set up the axis stream data, and then how does he transfer it to me, and then what he needs from me basically to receive it. So anyways, next. So these were the hurdles. So the first one was the axis stream test bench failed. That was the obvious one. Just took way too long. The second one was the time constraint. So we had a lot of features we wanted to implement, such as like signed filters, but it was going to take a little bit more logic in terms of the multipliers inside of there. You have to implement some logic to make sure that if it's a signed multiplication and if it's a negative value, you have to do a little bit more effort with 2's complement values. So we had to cut that out. And then we also had limitations in the FPGA hardware. So we think of the DMA can only be so big in terms of how big those the throughput is. So 128 bits. And then the other thing was that BRAM, for example, can only read two at a time. So we just cut that out very early in the project. And then other things were like, hey, if you're logic is too complicated. You're not going to be able to finish this project. So we just wanted to finish this overall and get it, working together, because the hardest part was actually interoperating between the processing side and also the programmable logic. So we had to really bash our heads together on that one. So you're good to go.
So this is on to the Pink subsystem. So like Trey said, I worked on the processing subsystem, which in essence is basically setting up the software side of things with convolution, but also interfacing with Trey's hardware over DMA. So with Pink, which allows us to it's basically an abstraction layer for the Zynq system on a chip, so that we can write software for the MCUs, but also hardware for the FPGA within it. So first, how we started off was reading images. And from those images, we have subsets within in the images, where going on to the CPU implementation, we can just apply filters and do convolution on each subset. For the FPGA implementation, though, we have to format each subset for DMA. And you'll see this as I continue talking about it a little more. So the image picker, may not seem like much, but we had to set it up so that it was easy for Trey to use, because basically Trey needed to use this to do his portion, since it links them up. So we did enumeration. So I scan an images directory and just enumerate every image. So again, this is easy to use, but it also makes the images iterable when reading. And so when reading the images, we can just iterate through each one in a for loop, since they're just values. And then we read them in grayscale to avoid complexity. Since this is just kind of proof of concept, we don't really need a 3-dimensional image. We can just do 2-dimensional. And what you see here is just a test image that we read in grayscale, which we use later on. And so building the convoluter, if you've done convolution before, this probably won't seem too exciting. But here we have our setup. So we have, so basically you have a stride of 1. So for each source pick, we're basically going a source pixel at a time, applying convolution. So we have our kernel here, and we're basically sliding it a source pixel at a time across our actual image. And once we do convolution, we store it into a new output buffer. And since the stride is 1, we do this, a pixel at a time. We did a 3x3 kernel, and there's no padding. So basically our output image is going to be a little bit smaller than an input. And I did a vertical filter just to test my convolution on my PC, which worked out. And this was just kind of a sanity check to make sure that it was working on the system on a chip, because it's a little harder to check there. And so building this, we would slide our kernel across the image and just store the results in a new output image. And the biggest thing about this, this is all necessary just to kind of, compare our software side of things to the hardware. But the biggest thing about this, for moving on to the next section, is that this is reusable for our framework for formatting DMA images, because a lot of this code could be reused for doing that. And so for formatting our image for DMA, what you see in this image is basically, our DMA interface. On the left side is what I did, which is the processing subsystem, and it just allows us to interface with DMA. So in essence, what we're able to do is through the images that we read in through the image picker, we're basically able to read the subsets of that image through DMA to memory, so that Trey's hardware extraction layer, or his IP for the hardware, can basically interface with those images. So what we need to do in the setup is read his overlay IP. From that, we can get basically the AXI stream IP, so I can actually interface with it. We needed to set up a 16-element buffer, each element being 8 bits. And so this buffer is going to store the subset of our images, or the subsets within our image. And then we needed in-out buffers for DMA transfer. The input buffer is so that we can actually transfer over DMA. And then the output buffer is to read back to ensure that it was actually transferred in the first place. And both of these buffers are 2-dimensional. So each row will store a subset from our image. So if you remember the last slide, instead of doing kernels this time, we're just doing subsets from our image. So we have 3x3 subsets that we're going to be reading into our input buffer. And so to build this, as we're iterating through our subsets, we basically copy each subset into a row of our input buffer, kind of like sliding the kernel across when doing convolution. We transfer this over DMA. And then we read it back into the output buffer. And this is just a sanity check to make sure that what we sent is also what we should receive. And this is essentially the interface with Tray's hardware so that you can actually apply the convolution. And then we get on to our results. So what you see here is an image from Tray's convolution. It's that same image that I tested against. And again, it's just a check to see if convolution is working. So whatever filter we applied here, that's what we got as the result. And over here, under this program execution, you can actually see, this is just basically the matrix showing that convolution data. Over here, however, this is testing. This isn't an actual image, but what you see here is just test data. And what you see below is actually seeing if, convolution is working over DMA. And so this is, again, just another sanity check. Before actually taking my image, Tray uses raw data to actually see if the convolution is working correctly. And it looks like he just adds up all the 4s and all the 2s, and it stores it into this new output image. So as a sanity check. And that's our project.
I mean, overall, the project result is very strong. Particularly, I'm very happy with Austin. I'm afraid that I was afraid that he may not have too much thing to say, but he did a very good job on the DMA part, particularly optimizing the interface between the FPGA and the DRAM is very important for the machine learning accelerators. Yes, this is good. Any question to them? If no, we can start. We can have the next group. Thank you.
Thank you.
Thank you.
I can do the presentation. Hey, this is Kai. I was doing the final report of the matrix multiplier. Recall what I have done before and what I do recently. In the past, I did the code to make the multiplier work and working with the intuitive clear diagram and research on the VHDL language concept to do the coding part. And what I have done in the past week, I recoded the VHDL code for the multiplier and the matrix, and I divided the diagram into like different part of the full adder, half adder, and the product, so it can be used to help me to record the coding, and then I adjust the code over and over to ensure that it could apply to a 16 bits or higher or with easy modification. And then I learn and use the loop concept of the VHDL. I finish the design code for the matrix multiplier and run the tester bench. This is the work. I divided the diagram into 6 parts, into 2 major parts, is a full adder and half adder. The half adder one is the edge of each line, as they have the same structure, to have 2 input of the X and Y and sum from the top line, and provide 2 output with 1 carry and 1 sum. These 3 half adder have the same pattern, and then another half adder, this half adder 2 is on top left. It's the last half adder, last half adder all in the first line. So I divided into an individual group. And then for the full adder, I divided it into a 3 group. The first full adder is in the first line. It's in the first line and not in the first, not the last, but in the between of the first line, as they have these two have the same structure of run the adder of 2 input of X and Y, and then provide the output, carry out, and sum to the next line. Then the full adder 3. Full adder 3 is the last full adder of the line is in, which are not in the first line. The full adder, the second line, and the last line. They are all the last full adder, as they also have the same pattern of having carrying from the last adder of the last line, and carry in from the full adder before them. They provide 2 output. One is the carry out, and one is the sum to the next full adder processing. And so these two also have the same pattern. And in the between is this 4 full adder. They have exactly the same pattern, as they also have the same XY input, sum input from the top, carry in from the right, and provide output to the left, carry out, and the next sum to the next full adder. So by dividing these 3 into a category, I recoded the recode. I do the recode and divided them into 2 half adder group and 3 full adder group to run the 4 loops. For the sum, I divided it into 4 groups also. One is the first digit of the result. This is a direct result from X0 and Y0. The sum 2 is the full adder. The second group is the full adder, is the half adder. These 3 half adders, as these also have the same pattern. And the last sum 4 is the carry out from this full adder, the last position of the full adder. And the rest sum is the collection of the last line full adder result. As shown here, also do the category organized different group and around do the loop and coding. This is the code before the recoding, and this will be the code that after the recoding. During the process, there's a lot of errors during the process, like this funny errors, and it's over and over. I do run the debugging and find the reason of the coding problem, and then I do after finish the coding improvement. The result is very good, and as shown here, every multiplier is getting the right result. And the working is that the problem that I faced is like lots of errors that blocks to run the test bench, like a syntax error and lots of others. and confused with the port connections. I need to connect different components together to like a full adder, half adder, or other multiplier together to run to make it function. And like a expression error and the index value error, lot of error that they need to be like a cost time and to do the research out to fix them. I learned the concept of VHDL code. I can create different components and connect them together, perform a task with a simpler code. Now the define type of arrays. To define a type of arrays that can help me to perform the task much easier. And it's very good for me to understand the format and the usage of for loops to reduce code needed for the general use of same code. And after the reason, another reason that I run the coding improvement is that it becomes very easy to adjust the multiplier to from 4-bit multiplier into a 8-bit multiplier by only adjusting the vectors of input and output, and there's a constraints that are defined in the complement, and then the test bench complement vector just adjust this vector. So these numbers I can run change the compiler from a 4-bit multiplier into a 8-bit multiplier, and it turns out it truly works. So the coding improvement can be further adjust and used into like a higher bit multiplier. Because this is the 4-bit multiplier and its result. This is the 8-bit multiplier that I run, and this is the result is correct after it's very correct, very nice result. And this is the schematic of the multiplier. Multiplier. It only performs the 4 bits by 4 bits multiplier. And the next is the matrix. This gives me a lot of trouble to run the matrix and to perform the tasks. But it turns out the code is very simple if I get the things right. This is a schematic design, and this picture that is showing the blue and the dot and the plus is the previous presentation, and it turns just around the multiplier dot product first, and around the header to add them together to can perform the result of each positions. And this is just a simple schematic design of the matrix multiplier. And in the code, the core code is very simple. To perform the tasks, well, I need to define and the position of each input, and find out the patterns of each the process. Where in the each of the lines is like a position 0, 0 times position B 0, 0, and add position 0, 1 and B 1 and 0. This is the main code, the core code, in the matrix, in the functions. While in the first part, you can show that I is the loop, J is also the loop. And when I is 0, you can see that the right part is 0, 1, 0, 1, 0, 1, 0, 1, no matter I change from 0 to 1. And while in the right B part, you can see that B keeps the right as 0, 1, 0, 1, no matter the B changes, no matter the position of J changes from 0 to 1. So it's much easier for me to understand how to code to make it function. The first line of the code is the first product of the two numbers, like 0, 0 times 0, 0. And the second line is the 0, 1 times 1, 0. So this becomes a unit that can be reused to perform tasks. Each block is the block of A and B is the result of the position. And during the process to make it work, I learned that the package is very good to define the matrix format of the data type of them in the matrix. As I run here, this is the input. I define the array of the input. It's a 4-byte input, 2x2 matrix, and this is the output. Is a 8 bits matrix, 2x2 matrix. It's very easy to define and use. We can show here. This is the 4 bits 2x2 array, and this is the 8 bits 2x2 array. This is the main code, just 2 for loops that can perform the task to calculate each position of the result of each position. And this is the test result that had performed. This is a 3, 2, 2, 3 matrix times the 1, 3, 3, 1 matrix. And the result is exactly what I do in the test bench. And this is the second test result is also the same. This is the third one. It's exactly the same. So it's very good result. And I do perform run the matrix multiplier works, make it works. And the further improvement, I consider to implement like a more controllable, like a clear or other method to make it connect to other component, and this can be a basic operation unit to help other project work. Thank you. That's all my presentation here.
Yeah, I believe the content is very concrete for a single person project. Any question to him? If no, do we have the last group?
Yeah, I think I'm the last group. I can do it like real fast if you want.
Okay.
Okay, let me share my screen. Can you guys see this?
Yes.
All right, so my name's Ryan. Go through this. I was focused on calculating heart rate. I'm getting a bachelor's in intelligence engineering this in like a week or so. The concentration in bioengineering. That's why most of my research is. So this hardware stuff's kind of new to me. VHDL is really new to me. So it's been fun learning that throughout the semester. And so kind of my project goals was just explore and study what it takes to code real-time FPGAs, VHDL, learn the process of how to code, debug, and design that. And then in terms of like module, what are things that I do? I wanted to design a clocked process for counting seconds, design a 4x4 binary multiplier. I ended up doing an 8x8 binary multiplier as well. I'll talk about that a little bit later. And also VHDL code to read a text file. I did not include it, but I did. I also started to work on doing a filter for some of the data, real-time data, but I did not get time to finish that, so I won't really talk about that here. But so the general premise is the input was heart rate variability data, and the output was the beats per minute at 15 seconds. I also did it for every second as well, but 15 seconds turned out to be more accurate, and I'll talk about that a little bit later as well. Problems and just like kind of like the lessons I've learned doing this project. I came here with mostly Python was like my coding language choice, really. And so I treating port maps kind of like a function, and that's not how it is. You can't just, you can't just make a lump of hardware exist and not exist based on different inputs. So you got to instantiate it and control the inputs going in and out of it. I learned that the hard way. I used the data type real. I'll talk about why that I decided to not do that. Learning debugging, and then I just making sure all these different components fit in good together was a really good lesson for me to learn. So in terms of solutions, this is the timer clock process I did before the midterm. So this is basically based on the idea of clock frequencies, oscillations per second. So it just counts how many rising edges are happening, and that's a second after it meets the clock frequency. So the result, you can see kind of the iteration here. And these seconds are going to be used to calculate the beats per minute, because it is literally beats per minute. So you have to consider the minutes part of it. And then this was I hate to admit it, but this took me longer than I expected to figure this out. So initially, I was taking heartbeats as just like a 1 or 0 type of signal. And that was not really the right way to do it, because in real time signal, you have, in between values, not necessarily 1 or 0. And so it's important to be able to do rise edge detection. So you have, the left side of the heartbeat and the peak, and you want to be able to detect that. You don't want to get the falling edge as well. And so this is the kind of the code, the major code format I did for this. So the first line is essentially taking my signal, which is the real-time data or the heartbeat, and kind of doing a 1-bit D flip-flop and to use it to delay my signal. And then the delay my signal compared with my signal is the edge detection line. So then I can tell whether the heartbeat has happened or not. And then I just detect if the rising my signal is equal to 1, and then I can count the heartbeats. So in terms of components, I won't talk about this too much because I feel like we are pretty confident in all. So this is a 4x4 binary multiplier. It's just adding and shifting. I ended up doing 8x8 because initially I was multiplying, because I was doing 15 seconds. I was multiplying by 4, so I'd count the beats per minute, the beats within 15 seconds, multiply 4, and obviously 4 you can do a 4x4. But then if I wanted to do per second, I'd have to multiply by 60, so therefore I would need an 8x8. Yes, so going on there, and then to talk about the kind of the signal in terms of like how I actually tested that all my components work together. So heart rate variability is the input signal in a sense. So the heart is controlled by the automatic nervous system. And so what makes that kind of interesting is you're the parasympathetic system kind of side of things, and you have just the sympathetic side of stuff. So the parasympathetic is kind of your rest. So it's what our heart rate variability is right now. Sympathetic is kind of the flight or fight response. And so that one actually kind of has interesting smooth heart rate variabilities compared to the parasympathetic ones, which is kind of interesting. But essentially, in terms of where these signals are coming from, the two most common ways to do it is ECGs or PPGs. ECGs are more accurate. They actually do the electrical signals. But of course, you have that electrode. So a lot of people don't like that. So PPPs are the most commonly used ones. So that's what you find in your Apple Watches, your other watches like do heart rates. That's light-based technology. And so this is the kind of inspiration for why I started to do a filter, because with these light-based system technologies, you get a lot of extra movement and it can cause a lot of noisy data. And so I wanted to do an IR filter to essentially reduce that, but I didn't have time to do that anyways. So moving on. So this was, I grabbed the Python library to get example heart rate signal peaks. So on the left is the output of it being plotted. My first thought process, which is a good learning process as well, is I was thinking, well, hardware is like to be, voltage 0 to 1. So I should normalize this, right? And so I normalized it, which turned out to be a bad decision. And I ended up going back to this, and I'll talk about that in the next slide. But the one thing I want to highlight is they already gave me what the beats per minute for this sample size was. It was 58.9. So I had something to compare against for when I calculated it myself with just the signal. First, I had to be able to read in a text file into VHDL, which turned out to be harder than expected. It took me a long time to realize that because when I was first doing this and I was trying to read in the heartbeat into the heartbeat temp function here, I wasn't getting anything at all, and I was wondering what was going on. It's because in my Python file I had an extra space, and it took me way too long to figure out that. But eventually I got it. But like I said, so over here is my normalized, which was not really great because you have to use real data types to be able to represent these floats in VHDL, and real data types are not synthesizable. So it's not really useful if you're going to make like a real-time data FPGA if you can't, synthesize it. So I decided to go back to just using these direct signals because I decided that, using an int of these amplitudes is actually not that terrible of a choice. So I went ahead and did that, which is where this logic kind of comes into, where I'm using, three different values of amplitude for the last different cycles. So I use one from 2 clock cycles ago, one from a previous clock cycle, and then the current amplitude. When I say amplitude, I'm talking about the actual values of the y-axis here. And so I use this to calculate whether a max has happened, so whether we're at a peak. So if the previous iteration is bigger than the one before it, and it's bigger than the one after it, so the current one, then we know it is a max. This is not a great solution down the road, especially if you have noisier systems, and because I had to pick a threshold in which to start this at. For a better solution, I think maybe like a ratio of comparing it would probably be best. But let's see, we're getting good time. Okay, 10 minutes. And then this is the final result. So this is just proof that it worked. You can see that my beats per minute ended up being 60, which is a little bit off from the 58.9. And I attribute that to this one goes through 25 seconds. Mine only goes to 15. So I associate kind of the error response with being a little bit different in here. But yeah, so that's my general result. I think for time's sake, I won't talk about my attempt at the IIR filter. But yeah, that's my project.
Okay, good. Thank you. How did you get your data set?
Yes, so I grabbed it. There's a Python library that has a sample data sets that you can pull. So this is a sample data set. I grabbed some other ones as well to make sure it wasn't just, working on just one.
So you actually get these data from online?
Yep.
Okay. Any question for him? If no question, you can email me after this class. You can email me, the rating of you for the other groups after this class. So this is our last class, and if you haven't done the OCQ, please do that. Thank you very much. Any question, you can ask me now, or you can email me. Thank you.
Thank you.
Thank you.
Thank you.